1 hour of space facts to fall asleep to. Welcome to our channel. Before starting, please like and subscribe for more stories. The universe as we know it is vast and awe-inspiring, stretching billions of light years across and containing billions of galaxies, stars, and planets. But how did it all begin? The most widely accepted scientific explanation for the origin of the universe is the Big Bang Theory, a groundbreaking idea that provides insight into the beginnings of space, time, and everything within them. The story of the universe's origin takes us back approximately 13.8 billion years to a moment of unimaginable density and heat. Before the Big Bang, the universe as we know it didn't exist. In fact, the term before itself is misleading because time and space came into existence only with a Big Bang. According to this theory, the universe began as a singularity, a point of infinite density and temperature where all matter and energy were compressed into an incredibly small space. This singularity suddenly began to expand in an event known as the Big Bang, creating the fabric of space and time itself. The term Big Bang might imply a violent explosion, but it was not an explosion in space. It was an expansion of space itself. Imagine a balloon with dots on its surface. As the balloon inflates, the dots move farther apart. Similarly, the Big Bang was the rapid stretching of space, causing everything within the universe to move away from everything else. In the first fractions of a second after the Big Bang, the universe was unimaginably hot and dense, filled with a seething soup of energy and fundamental particles. During this period, known as the Planck era, the forces of nature, gravity, electromagnetism, and nuclear forces were unified into a single force. As the universe expanded and cooled, these forces began to separate, and particles like quarks and electrons started to form. About 1 second after the Big Bang, quarks combined to form protons and neutrons, the building blocks of atoms. As the universe continued to cool, these protons and neutrons fused together during a process called nucleosynthesis, forming the nuclei of light elements like hydrogen and helium. However, it would take hundreds of thousands of years before these nuclei could capture electrons to form neutral atoms. This early period of the universe, often referred to as the cosmic dark ages, was a time when no stars or galaxies had yet formed. The universe was filled with a diffuse cloud of gas, and light was unable to travel freely because it kept scattering off charged particles. This changed about 380,000 years after the Big Bang, when the universe had cooled enough for electrons to combine with nuclei, forming neutral atoms in a process known as recombination. This event allowed light to travel freely for the first time, creating what we now observe as the cosmic microwave background radiation, CMB, a faint glow that permeates the universe and provides a snapshot of the early cosmos. One of the strongest pieces of evidence supporting the Big Bang theory is the discovery of cosmic microwave background radiation. First detected in 1964 by Arno Penzias and Robert Wilson, the CMB is the remnant radiation from the Big Bang. It is a faint, almost uniform glow of microwave energy that fills the entire sky, and its properties match the predictions made by the Big Bang theory. Another key piece of evidence comes from the expansion of the universe, first observed by Edwin Hubble in the 1920s. Hubble discovered that galaxies are moving away from us, with their light redshifted due to the expansion of space. This observation led to the realization that the universe is not static but is constantly growing larger, as predicted by the Big Bang model. Additionally, the relative abundances of light elements like hydrogen, helium, and lithium in the universe align with the predictions of Big Bang nucleosynthesis. These elements were formed during the first few minutes after the Big Bang and serve as a cosmic fingerprint of the event. After the formation of neutral atoms, gravity began to take over, pulling gas and dark matter together to form the first structures in the universe. Over hundreds of millions of years, small clumps of matter grew into larger structures, eventually forming stars, galaxies, and clusters of galaxies. The first stars, known as population 3 stars, were massive and short-lived, producing heavy elements through nuclear fusion and supernova explosions. These elements would later become the building blocks of planets and life. The formation of galaxies, such as the Milky Way, marked the next major milestone in the evolution of the universe. Galaxies are massive systems of stars, gas, dust, and dark matter bound together by gravity. Within these galaxies, stars continue to form, burn their fuel, and die, enriching the surrounding environment with heavier elements. One of the most intriguing discoveries of the past century is that the universe is not only expanding, but doing so at an accelerating rate. This acceleration is attributed to a mysterious force called dark energy, which makes up about 68% of the universe's total energy content. While scientists have yet to understand the true nature of dark energy, its effects are undeniable. It is driving galaxies farther apart and shaping the future of the cosmos. The ultimate fate of the universe depends on the balance between dark energy and gravity. If dark energy continues to dominate, the universe may expand forever in a scenario known as the Big Freeze, where galaxies, stars, and eventually atoms themselves will drift apart, leaving a cold, dark cosmos. Alternatively, if the expansion slows and reverses, the universe could collapse back into a singularity in a big crunch. Some theories even propose a cyclic model, where the universe undergoes endless cycles of expansion and contraction. Today, scientists use advanced telescopes and experiments to study the universe's origins and evolution. The James Webb Space Telescope, JWST, launched in 2021, is capable of observing the faint light from some of the earliest galaxies, providing new insights into the infancy of the universe. Meanwhile, particle accelerators like the Large Hadron Collider, LHC, help scientists recreate conditions similar to those of the Big Bang, shedding light on the fundamental forces and particles that govern the cosmos. The story of the Big Bang is not just about the origins of the universe. It is a tale of transformation, complexity, and the interconnectedness of all things. From a singular point of infinite density to the vast, intricate cosmos we see today, the universe's journey is a testament to the power of natural forces and the curiosity of humanity. As scientists continue to explore the depths of space and time, we move closer to understanding the mysteries of our cosmic origins and our place within this extraordinary universe. The universe is a vast, intricate, and mind-bogglingly large system that continues to fascinate and challenge our understanding. Its structure is both grand and delicate, with galaxies, clusters, and voids forming a cosmic tapestry that stretches across billions of light-years. While it may seem chaotic at first glance, the universe is governed by the fundamental forces of physics, creating patterns and structures that reflect its dynamic and evolving nature. The part of the universe we can observe is known as the observable universe, which spans about 93 billion light-years in diameter. This limit exists because the speed of light determines how far we can see. Light from distant objects takes time to reach us, and the universe itself has a finite age of 13.8 billion years. Beyond the observable universe lies a vast expanse of space we cannot currently detect, but which likely continues in much the same way as the region we can see. The observable universe contains an estimated 2 trillion galaxies, each composed of billions to trillions of stars, along with gas, dust, and dark matter. Within these galaxies are planetary systems, black holes, and other celestial objects that contribute to the cosmic diversity. Despite its immense size, the universe is largely empty, with vast stretches of space separating these structures. At the heart of the universe's structure are galaxies, massive systems of stars, gas, dust, and dark matter held together by gravity. Galaxies come in various shapes and sizes, including 1. Spiral galaxies. These galaxies, like our Milky Way, feature a flat, rotating disk with spiral arms radiating outward from a central bulge. Spiral galaxies often contain young, bright stars in their arms and older stars in their cores. 2. Elliptical galaxies. These are more spherical or oval-shaped, with little gas and dust. They contain mostly older stars and lack the prominent structures seen in spiral galaxies. 3. Irregular galaxies. As their name suggests, these galaxies lack a defined shape, often due to gravitational interactions or collisions with other galaxies. The Milky Way galaxy, where our solar system resides, is a spiral galaxy that measures about 100,000 light-years across. It contains approximately 200 to 400 billion stars and is home to a supermassive black hole at its center known as Sagittarius A star. Galaxies like the Milky Way are often part of larger cosmic structures, forming clusters and superclusters. Galaxies are not isolated entities. They are often grouped together in galaxy clusters, which can contain hundreds or even thousands of galaxies bound by gravity. For example, the Virgo cluster, located about 65 million light-years away, is a prominent cluster in our local cosmic neighborhood. On an even larger scale, clusters themselves are grouped into superclusters, the largest structures in the universe. The Milky Way is part of the local group, which in turn is part of the Laniakea supercluster, a massive structure containing thousands of galaxies. The universe's largest scale structure is often described as a cosmic web, a network of filaments composed of galaxies and clusters connected by vast threads of gas and dark matter. These filaments are separated by enormous voids, regions of space that contain very few galaxies or matter. This web-like structure was shaped by gravity over billions of years, as matter coalesced into denser regions while expanding outward into the voids. One of the most mysterious components of the universe is dark matter, an invisible substance that makes up about 27% of the universe's total mass energy content. Although dark matter cannot be seen directly, its presence is inferred from its gravitational effects on galaxies and clusters. For example, galaxies rotate at speeds that cannot be explained by the visible matter they contain, suggesting the presence of an unseen mass. Dark matter acts as the scaffolding of the universe, providing the gravitational pull necessary for galaxies and large-scale structures to form and remain stable. Without dark matter, the universe as we know it would look vastly different. Scientists are still searching for direct evidence of dark matter, using experiments like the Large Hadron Collider, LHC, and specialized detectors buried deep underground. While dark matter helps hold the universe together, another mysterious force, known as dark energy, is driving it apart. Dark energy makes up about 68% of the universe's total mass energy content and is responsible for the accelerating expansion of the universe. This phenomenon was discovered in the late 1990s through observations of distant supernovae, which show that galaxies are moving away from each other at an increasing rate. The exact nature of dark energy remains one of the greatest mysteries in cosmology. It is often associated with a cosmological constant, a term introduced by Albert Einstein to describe the energy density of empty space. However, other theories suggest that dark energy could be a dynamic field or a manifestation of unknown physics. The interplay between dark energy and gravity will determine the ultimate fate of the universe. If dark energy continues to dominate, the universe may expand forever in a scenario called the Big Freeze, where galaxies, stars, and eventually atoms will drift apart, leaving a cold and dark cosmos. Gravity is the fundamental force that governs the structure and evolution of the universe. It is responsible for pulling matter together to form stars, planets, and galaxies, as well as for shaping the large-scale structures we observe today. The interplay between gravity and other forces, such as the expansion driven by dark energy, creates the dynamic and ever-changing cosmos. Einstein's general theory of relativity revolutionized our understanding of gravity, describing it as the curvature of space-time caused by mass and energy. This theory has been instrumental in explaining phenomena such as black holes, gravitational lensing, and the expansion of the universe. Modern telescopes and observatories allow scientists to map and study the structure of the universe in unprecedented detail. Instruments like the Hubble Space Telescope and the James Webb Space Telescope, JWST, provide images of distant galaxies and clusters, revealing how cosmic structures evolved over billions of years. Meanwhile, large-scale surveys, such as the Sloan Digital Sky Survey (SDSS), create 3D maps of galaxies and cosmic filaments, offering insights into the distribution of matter. The structure of the universe is a testament to the power of natural forces and the intricate interplay between matter, energy, and time. From the smallest scales of galaxies to the vast expanse of the cosmic web, the universe's architecture reflects billions of years of evolution. As scientists continue to explore and unravel the mysteries of the cosmos, we gain a deeper appreciation for the beauty, complexity, and unity of the universe we call home. Stars are the building blocks of the universe, providing light, heat, and the energy necessary for life to exist. They are formed from massive clouds of gas and dust, and undergo a fascinating life cycle governed by the interplay of gravity, pressure, and nuclear fusion. Stars come in many shapes, sizes, and colors, ranging from tiny, dim red dwarfs to massive, blazing blue supergiants. Each type of star lives a unique life, from its birth in a nebula to its eventual death, which may result in a white dwarf, neutron star, or black hole. Understanding the life cycle of stars gives us a window into the processes that shape the cosmos and create the elements essential for life. Stars are born in nebulae, vast clouds of gas and dust that serve as stellar nurseries. These regions are often triggered into star formation by external events, such as the shock waves from a nearby supernova or the gravitational interaction of galaxies. When parts of a nebula become denser, gravity begins to pull the gas and dust together into clumps. Over time, these clumps grow larger and collapse under their own gravity, forming protostars, the earliest stage of a star's life. As the protostar contracts, its core temperature and pressure increase. Eventually, when the core temperature reaches about 10 million Kelvin, nuclear fusion begins. This process converts hydrogen into helium, releasing an enormous amount of energy and halting the protostar's collapse. At this point, the star enters the main sequence phase, the longest and most stable period of its life. During the main sequence phase, a star achieves a balance between the inward pull of gravity and the outward pressure generated by nuclear fusion. This equilibrium allows the star to maintain a stable size and shine steadily for millions to billions of years, depending on its mass. Low-mass stars, such as red dwarfs, burn their hydrogen fuel slowly and can remain in the main sequence for tens of billions of years. In contrast, massive stars, like blue giants, burn through their fuel much more quickly and may leave the main sequence after just a few million years. Our Sun is a typical main sequence star, classified as a G-type yellow dwarf. It has been in the main sequence for about 4.6 billion years and is expected to remain stable for another 5 billion years. During this phase, nuclear fusion in the Sun's core produces the light and heat that sustain life on Earth. When a star exhausts the hydrogen in its core, nuclear fusion slows, and gravity causes the core to contract. This contraction heats the core further, igniting the fusion of helium into heavier elements like carbon and oxygen. Meanwhile, the outer layers of the star expand dramatically, and the star becomes a red giant or supergiant, depending on its initial mass. For stars like the Sun, the red giant phase is a brief but spectacular period of expansion. The Sun will eventually swell to many times its current size, potentially engulfing the inner planets, including Earth. In this phase, the star loses much of its outer material through stellar winds, creating a beautiful and luminous planetary nebula. Massive stars, on the other hand, become red or blue supergiants and undergo a much more explosive demise. These stars can fuse heavier elements like silicon and iron in their cores, but once iron forms, no further energy can be produced through fusion. This signals the star's impending death in a dramatic supernova explosion. The fate of a star depends on its mass. Low-mass stars, like red dwarf, low-mass stars burn their fuel very slowly and eventually fade into white dwarfs, dense remnants about the size of Earth. These stars emit residual heat for billions of years before cooling into faint, dark objects known as black dwarfs. Intermediate mass stars, like the Sun, after shedding their outer layers as a planetary nebula, intermediate mass stars leave behind a white dwarf core. These white dwarfs are composed mostly of carbon and oxygen, held together by electron degeneracy pressure. They do not undergo further fusion and slowly cool over time. Massive stars, more than 8 solar masses. Massive stars end their lives in a supernova, one of the most powerful explosions in the universe. The core of the star collapses, forming either a neutron star or a black hole, depending on the remaining mass. Neutron stars are incredibly dense, with a teaspoon of neutron star material weighing billions of tons. Some neutron stars become pulsars, emitting beams of radiation as they spin rapidly. If the star's core is massive enough, it collapses further into a black hole, a region of space where gravity is so intense that not even light can escape. Black holes often consume surrounding material, releasing immense energy in the process and influencing their cosmic environment. The life cycle of stars gives rise to some of the most fascinating phenomena in the universe. Supernovae. These explosions not only mark the death of massive stars, but also play a crucial role in enriching the universe with heavy elements like gold, silver, and uranium. These elements are scattered into space, where they become part of new stars, planets, and even life. Pulsars, rapidly rotating neutron stars, emit beams of radiation that appear to pulse as the star spins. Pulsars are among the most precise cosmic clocks in the universe, with some spinning hundreds of times per second. Binary star systems. Many stars exist in pairs or systems of multiple stars. In some cases, material from one star may be drawn onto another, creating phenomena like novae or even triggering supernovae. Stars are not just brilliant points of light in the night sky. They are the forges where the elements essential for life are created. Through the process of stellar nucleosynthesis, stars produce elements like carbon, oxygen, and nitrogen, which are necessary for the formation of planets and living organisms. These elements are released into space when stars die, becoming part of the cosmic material that forms new stars, planets, and eventually life. Our own sun, like many other stars, is part of a lineage that stretches back to earlier generations of stars. The atoms in your body were forged in the heart of a star billions of years ago, making us all literally made of star stuff, as the famous astronomer Carl Sagan once said. The life cycle of a star, from its birth in a nebula to its eventual death, is a testament to the dynamic and ever-changing nature of the universe. Stars are not eternal, but their legacy endures in the elements they create and the light they leave behind. As we study these celestial objects, we gain a deeper understanding of the cosmos and our place within it. The story of stars is ultimately the story of the universe itself, a story of creation, transformation, and renewal that continues to unfold across billions of years. Black holes and neutron stars represent the most extreme outcomes of stellar evolution, showcasing the universe at its most mysterious and powerful. These celestial objects are born from the death of massive stars, and they push the limits of physics, gravity, and our understanding of the cosmos. While black holes are regions of space where gravity is so strong that nothing, not even light, can escape, neutron stars are incredibly dense remnants of stars that pack more mass than the Sun into a sphere only a few kilometers across. Let's dive deeper into these fascinating phenomena. Both black holes and neutron stars originate from the collapse of massive stars at the end of their life cycles. When a star exhausts the nuclear fuel in its core, it can no longer resist the inward pull of gravity. For stars with masses greater than about 8 times the mass of the Sun, this collapse results in one of two outcomes, depending on the remaining mass of the core after a supernova explosion. 1. Neutron stars. If the remaining core has a mass between about 1.4 and 3 solar masses, the collapse is halted by neutron degeneracy pressure, a quantum mechanical effect that arises from the repulsion between tightly packed neutrons. The result is an incredibly dense object called a neutron star, which has a diameter of only about 10 to 20 kilometers but a mass greater than the Sun. 2. Black holes. If the core's mass exceeds about 3 solar masses, gravity overwhelms all opposing forces, and the core continues to collapse into a singularity, a point of infinite density. The region around the singularity where gravity becomes so intense that nothing can escape is called the event horizon, marking the boundary of a black hole. Neutron stars are among the densest objects in the universe. To put their density into perspective, a sugar cube-sized amount of neutron star material would weigh billions of tons on Earth. These stellar remnants are composed almost entirely of neutrons, with their interiors resembling a giant atomic nucleus. Some neutron stars have magnetic fields that are trillions of times stronger than Earth's. When they rotate rapidly, they emit beams of electromagnetic radiation from their magnetic poles, becoming pulsars. These beams sweep across space like lighthouse beams, and when observed from Earth, they appear as periodic flashes of light. Pulsars are incredibly precise, with some spinning hundreds of times per second, making them nature's most accurate clocks. A special type of neutron star is the magnetar, which has an extraordinarily powerful magnetic field, up to a quadrillion times stronger than Earth's. Magnetars are rare and can release sudden bursts of energy that disrupt their surroundings, including nearby stars and spacetime. Black holes are even more enigmatic than neutron stars. Defined by their event horizon, black holes are regions where gravity is so strong that not even light can escape, making them invisible to direct observation. Instead, their presence is inferred by the way they affect nearby objects, such as stars, gas, and dust. There are several types of black holes. 1. Stellar black holes. These form from the collapse of massive stars and typically have masses between 3 and 20 times that of the Sun. They are often found in binary systems, where they can accrete material from a companion star, forming an accretion disk that emits intense radiation. Two supermassive black holes, found at the centers of most galaxies, including the Milky Way. These black holes have masses ranging from millions to billions of times the mass of the Sun. The Milky Way's supermassive black hole, Sagittarius A*, has a mass equivalent to about 4 million suns. Three intermediate black holes. These are thought to bridge the gap between stellar and supermassive black holes, with masses in the range of hundreds to thousands of solar masses. Their formation and existence remain an active area of research. For primordial black holes, hypothetical black holes that may have formed in the early universe due to fluctuations in density. These could range in size from microscopic to massive, and they remain speculative. The defining feature of a black hole is its event horizon, beyond which nothing can escape. The distance from the event horizon to the singularity depends on the black hole's mass, and this region is known as the Schwarzschild radius. Within this radius, spacetime is so curved that all paths lead inward to the singularity. Black holes also exhibit other fascinating phenomena. Gravitational time dilation. Near a black hole, time slows down relative to an observer farther away. This effect, predicted by Einstein's general theory of relativity, means that for someone near a black hole, seconds could pass while years go by for a distant observer. Hawking radiation. Proposed by physicist Stephen Hawking, this theoretical process suggests that black holes can emit particles due to quantum effects near the event horizon. Over immense periods, this could cause black holes to lose mass and eventually evaporate. Both black holes and neutron stars play significant roles in the cosmos. 1. Stellar evolution. They are the endpoints of massive stars, marking the final stages of stellar evolution and enriching the universe with heavy elements formed in supernova explosions. 2. Gravitational influence. Black holes and neutron stars influence their surroundings through their immense gravitational pull, shaping the motion of stars, gas, and dust in their vicinity. 3. Astrophysical laboratories. These objects serve as natural laboratories for studying the extremes of physics, from the behavior of matter under extreme pressure in neutron stars to the nature of spacetime around black holes. 4. Cosmic mergers. When neutron stars or black holes collide, they produce gravitational waves, ripples in spacetime that were first detected by the LIGO and Virgo observatories in 2015. These events also release massive amounts of energy, creating phenomena like kilonovae, which forge heavy elements like gold and platinum. Despite their elusive nature, black holes and neutron stars can be studied through indirect means. X-ray emissions. When material falls into a black hole or is compressed on the surface of a neutron star, it emits X-rays, which can be detected by space telescopes like Chandra and XMM Newton. Gravitational waves. The collision of black holes or neutron stars generates gravitational waves, which carry information about these cataclysmic events. Event Horizon Telescope, EHT, in 2019, the EHT captured the first-ever image of a black hole located in the center of the galaxy Messier 87. This achievement provided visual confirmation of black holes' existence and offered insights into their behavior. Black holes and neutron stars are among the most fascinating objects in the universe, representing the extremes of density, gravity, and energy. They challenge our understanding of physics and offer glimpses into the fundamental nature of reality. The solar system is our cosmic neighborhood, a vast and fascinating system dominated by the sun and home to planets, moons, asteroids, comets, and countless other objects. Formed around 4.6 billion years ago, it offers a window into the processes that govern the universe, from the birth of stars to the formation of planetary systems. While we've explored only a fraction of its wonders, the solar system remains a focus of scientific discovery, sparking curiosity and expanding our understanding of the cosmos. The solar system began as a giant molecular cloud composed of gas and dust. A nearby supernova or some other cosmic event likely triggered the collapse of this cloud, causing it to spin and flatten into a protoplanetary disk. At the center of this disk, the Sun formed, igniting through nuclear fusion and becoming the system's primary source of energy. Around the Sun, the remaining material coalesced into planets, moons, and other objects through a process called accretion. The composition of the protoplanetary disk determined the layout of the solar system. Close to the Sun, only rocky materials could withstand the intense heat, leading to the formation of the terrestrial planets Mercury, Venus, Earth, and Mars. Farther out, where temperatures were cooler, gas and ice giants, Jupiter, Saturn, Uranus, and Neptune formed, surrounded by rings and dozens of moons. Beyond Neptune lies the Kuiper Belt, a region of icy bodies, and even farther, the Oort cloud, the source of long-period comets. The Sun, a yellow dwarf star, is the solar system's central hub. Comprising over 99.8% of the system's total mass, it exerts gravitational control over all other objects. The Sun generates energy through the fusion of hydrogen into helium in its core, releasing light and heat that sustain life on Earth. The Sun's structure is layered, with the core as its power source, surrounded by the radiative and convective zones, and topped by the photosphere, the visible surface. The outer layers include the chromosphere and the corona, the latter being visible during solar eclipses. The Sun's magnetic activity gives rise to phenomena such as sunspots, solar flares, and coronal mass ejections, which can affect Earth's technology and atmosphere. The inner solar system is home to the terrestrial planets, small rocky worlds with solid surfaces. 1. Mercury, the closest planet to the Sun. Mercury is a barren, cratered world with extreme temperature fluctuations. Its thin atmosphere, called an exosphere, offers little protection from solar radiation. 2. Venus, often called Earth's twin due to its similar size and composition, Venus is a hellish world with a thick atmosphere of carbon dioxide and clouds of sulfuric acid. Its surface temperature exceeds 460 degrees Celsius, 860 degrees Fahrenheit, making it the hottest planet in the solar system. 3. Earth, the only planet known to support life. Earth has a diverse climate, a protective atmosphere, and abundant liquid water. Its magnetic field shields it from harmful solar radiation, and its moon plays a vital role in stabilizing its axial tilt and creating tides. 4. Mars, known as the Red Planet due to its iron-rich soil, Mars has polar ice caps, the largest volcano in the solar system, Olympus Mons, and a massive canyon system, Valles Marineris. While its atmosphere is thin, evidence of ancient riverbeds suggests it once had liquid water. The outer solar system is dominated by the gas giants and ice giants, massive planets surrounded by rings and moons. 1. Jupiter, the largest planet in the solar system. Jupiter has a strong magnetic field and at least 92 moons, including Ganymede, the largest moon in the solar system. Its famous Great Red Spot is a massive storm that has raged for centuries. 2. Saturn, known for its iconic ring system. Saturn is a gas giant with dozens of moons, including Titan, which has a thick atmosphere and liquid methane lakes. Saturn's rings are made of ice and rock particles. 3. Uranus, an ice giant with a bluish-green hue due to methane in its atmosphere. Uranus rotates on its side, possibly due to a collision with a massive object. Its moons and faint rings add to its intrigue. 4. Neptune, the farthest planet from the Sun. Neptune is another ice giant with intense winds and storms, including the Great Dark Spot. Its moon Triton orbits in the opposite direction of Neptune's rotation, suggesting it was captured from the Kuiper Belt. Beyond Neptune lies the Kuiper Belt, a region populated by icy objects, dwarf planets, and short-period comets. The most famous of these is Pluto, which was reclassified as a dwarf planet in 2006. Pluto has a thin atmosphere and a complex surface featuring plains, mountains, and possible ice volcanoes. Other notable dwarf planets include Eris, slightly smaller than Pluto, and Haumea, known for its elongated shape. The Kuiper Belt is also home to comets, which develop glowing tails when they approach the Sun. The solar system is teeming with moons, each with unique features. Earth's moon, essential for stabilizing Earth's tilt and creating tides. It also served as humanity's first destination beyond our planet during the Apollo missions. Europa, Jupiter, an icy moon with a subsurface ocean, making it a prime candidate for the search for extraterrestrial life. Titan, Saturn, known for its thick atmosphere and methane lakes. Titan has conditions that resemble early Earth. Io, Jupiter, the most volcanically active body in the solar system, with hundreds of active volcanoes. The solar system is also home to smaller objects. Asteroids, rocky bodies mostly found in the asteroid belt between Mars and Jupiter. Some, like Ceres, are large enough to be considered dwarf planets. Comets, icy bodies from the Kuiper Belt and Oort cloud that develop glowing tails when they approach the sun. Meteoroids, smaller fragments of asteroids or comets. When they enter Earth's atmosphere and burn up, they are called meteors, and if they reach the surface, they are meteorites. Humanity has sent numerous probes to explore the solar system, revealing its wonders. Voyager 1 and 2. These spacecraft, launched in 1977, have traveled beyond the heliosphere and are providing data about interstellar space. Mars rovers, missions like Perseverance and Curiosity, have uncovered evidence of water and potential habitability on Mars. Cassini-Huygens. This mission studied Saturn and its moons, including Titan and Enceladus. New Horizons. The first mission to explore Pluto and the Kuiper Belt, providing unprecedented insights into these distant regions. The solar system is not just our home. It is a cosmic laboratory that offers clues about the origins of planets, the potential for life beyond Earth, and the fundamental forces that shape the universe. As we continue to explore, we uncover new mysteries and deepen our understanding of the dynamic system we call home. The Moon, Earth's only natural satellite, has captivated humanity for millennia, serving as a beacon of wonder, inspiration, and scientific discovery. Its influence on Earth extends far beyond its ethereal beauty in the night sky. From stabilizing Earth's rotation to driving ocean tides, the Moon plays a critical role in maintaining conditions that make our planet habitable. Over the past century, the Moon has also become a focal point for space exploration, representing humanity's first steps beyond Earth and our aspirations for deeper cosmic ventures. The Moon is believed to have formed about 4.5 billion years ago, shortly after the birth of the solar system. The most widely accepted theory, known as the giant impact hypothesis, suggests that the Moon was created when a Mars-sized body, often referred to as Theia, collided with a young Earth. This catastrophic impact ejected massive amounts of debris into orbit around Earth. Over time, this material coalesced to form the Moon. This theory explains many of the Moon's unique characteristics, such as its lower density compared to Earth and its similar composition of certain isotopes. The Moon's initial surface was likely covered in a molten ocean, which gradually cooled and solidified, forming the rugged landscape we see today. The Moon is a relatively small celestial body, with a diameter of about 3,474 kilometers, 2,159 miles, roughly one-quarter the size of Earth. Despite its size, its proximity to Earth, about 384,400 kilometers, 238,855 miles on average, makes it the brightest object in our night sky. The Moon has no significant atmosphere, which means there is no weather, no erosion from wind or rain, and extreme temperature fluctuations between day and night. The surface of the Moon is characterized by highlands, maria, and craters. Highlands. These lighter regions are older, heavily cratered, and make up most of the Moon's surface. Maria, the darker, smoother plains, are vast basaltic regions formed by ancient volcanic activity. The term Maria means seas in Latin, as early astronomers mistakenly thought they were actual bodies of water. Craters. The Moon's surface is pockmarked with craters formed by asteroid and comet impacts over billions of years. Some, like the Tycho crater, are visible to the naked eye from Earth. The Moon has a profound impact on Earth, influencing both its physical and biological processes. Tides, the Moon's gravitational pull creates the ocean tides, which play a crucial role in shaping coastal ecosystems and supporting marine life. Tidal forces also help stabilize Earth's climate by redistributing heat across the planet. 2. Axial stability. The Moon's gravitational interaction with Earth helps stabilize the planet's axial tilt, which varies only slightly over time. Without the Moon, Earth's tilt could fluctuate wildly, leading to extreme changes in climate that could make the planet less hospitable for life. 3. Lengthening days. Over billions of years, the Moon's gravitational pull has gradually slowed Earth's rotation, increasing the length of our days. When the Moon first formed, a day on Earth may have been as short as 6 hours. The Moon has been a target of human curiosity for centuries, but it wasn't until the 20th century that humanity made its first steps on its surface. The Apollo program, conducted by NASA between 1961 and 1972, stands as one of the greatest achievements in human history. Apollo 11, 1969, Neil Armstrong and Buzz Aldrin became the first humans to walk on the moon, delivering the famous words, "That's one small step for man, one giant leap for mankind." This mission provided invaluable data about the moon's geology and composition. Subsequent Apollo missions explored other lunar regions, collected rock samples, and conducted experiments, helping scientists understand the moon's history and its connection to Earth. In recent years, interest in the moon has surged again, with plans for further exploration and even colonization. Programs like NASA's Artemis aim to return humans to the lunar surface, with the goal of establishing a sustainable presence that could serve as a stepping stone for missions to Mars and beyond. The lack of an atmosphere on the moon means that its surface has remained largely unchanged for billions of years. This makes it an invaluable time capsule for studying the early solar system. The moon's rocks and regolith, a layer of loose, fragmented material, hold clues about the period of heavy bombardment when Earth and other planets were frequently struck by asteroids and comets. Studying the moon helps scientists better understand the history of our solar system and the processes that shape planetary bodies. The moon plays a central role in one of nature's most awe-inspiring phenomena, eclipses. A solar eclipse occurs when the moon passes directly between Earth and the sun, casting a shadow on Earth. A lunar eclipse, on the other hand, occurs when Earth passes between the sun and the moon, causing Earth's shadow to fall on the moon. These events have not only fascinated humans for centuries, but also played a critical role in advancing our understanding of celestial mechanics. Throughout history, the moon has held a special place in human culture, mythology, and science. Ancient civilizations used the moon to measure time and create calendars, while poets and artists have drawn inspiration from its silvery glow. The moon is also a central figure in many myths, often symbolizing fertility, transformation, or mystery. Looking ahead, the moon is set to play a key role in humanity's future in space. Plans for lunar bases and mining operations could provide the resources needed for long-term space exploration. For example, the moon's regolith contains helium-3, a rare isotope that could be used in advanced nuclear fusion technologies. Additionally, the discovery of water ice in permanently shadowed craters at the moon's poles has opened up possibilities for producing oxygen, drinking water, and rocket fuel. The moon is more than just a celestial body orbiting Earth. It is a vital part of our planet's story and future. Its gravitational influence, historical significance, and potential as a platform for exploration make it one of the most important objects in the solar system. As we continue to study and explore the moon, it will remain a symbol of human curiosity and ambition, reminding us of our place in the vast cosmos. The search for planets beyond our solar system, known as exoplanets, has revolutionized our understanding of the universe and raised profound questions about the possibility of life elsewhere. Since the discovery of the first exoplanet orbiting a sun-like star in 1995, scientists have identified over 5,000 exoplanets, with more being discovered every year. These planets come in a dazzling variety of sizes, compositions, and orbital configurations, challenging traditional ideas of planetary formation and habitability. The quest to study exoplanets is not just about cataloging distant worlds. It's a search for answers to some of humanity's oldest questions. Are we alone in the universe? How common is life among the stars? Exoplanets are planets that orbit stars outside our solar system. They range from hot Jupiters, massive gas giants orbiting close to their stars, to super-Earths, rocky planets larger than Earth but smaller than Neptune. These worlds differ dramatically from the planets in our own solar system, demonstrating the diversity of planetary systems across the galaxy. One of the most critical aspects of studying exoplanets is determining whether they fall within the habitable zone, often called the Goldilocks zone. This is the region around a star where conditions are just right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. Detecting exoplanets is a challenging task because they are incredibly distant, dim, and often lost in the glare of their parent stars. However, astronomers have developed ingenious methods to find and study these distant worlds. 1. Transit method. The most successful technique involves observing a star's brightness for periodic dips, which occur when a planet passes in front of the star or transit. NASA's Kepler Space Telescope used this method to discover thousands of exoplanets by monitoring the light curves of distant stars. 2. Radial velocity method. This method measures the wobble of a star caused by the gravitational pull of an orbiting planet. The wobble causes shifts in the star's spectral lines, which can be detected using sensitive instruments. 3. Direct imaging. In rare cases, exoplanets can be directly photographed using powerful telescopes equipped with coronagraphs to block out the star's light. This method is more effective for large planets orbiting far from their stars. For gravitational microlensing, this technique uses the gravitational field of a star and its planet to magnify the light of a more distant background star. It is particularly useful for detecting planets in regions of the galaxy far from Earth. Over the years, several exoplanets have captured the imagination of scientists and the public alike. Kepler-22b, one of the first potentially habitable exoplanets discovered, Kepler-22b lies about 600 light-years away and is located in its star's habitable zone. While its composition remains uncertain, its size suggests it could be a water-rich world or a rocky planet with a thick atmosphere. Proxima Centauri b. This planet orbits Proxima Centauri, the closest star to our solar system, just 4.24 light-years away. Located within the habitable zone, Proxima Centauri b has sparked interest as a possible target for future interstellar missions. TRAPPIST-1 system. This system, located 40 light-years away, contains 7 Earth-sized planets orbiting a red dwarf star. 3 of these planets are in the habitable zone, making TRAPPIST one of the most intriguing systems for the search for extraterrestrial life. 55 Cancri e. This super-Earth, located 41 light-years away, is a volcanic inferno with surface temperatures that can melt rock. It is thought to have a thick atmosphere and may provide insights into the diversity of rocky planets. One of the most exciting goals of exoplanet research is the search for biosignatures, chemical or physical markers that can indicate the presence of life. These include oxygen and ozone. High levels of oxygen in a planet's atmosphere, along with ozone, a product of oxygen, could be a sign of photosynthetic life. Methane. Methane can be produced biologically, especially when found alongside oxygen in an atmosphere. Water vapor. The presence of water vapor in a planet's atmosphere suggests the potential for liquid water on its surface. Unusual light reflections. Changes in light reflected from a planet could indicate vegetation or other biological processes. Telescopes like the James Webb Space Telescope, JWST, and upcoming missions such as LUVOIR and European Extremely Large Telescope, ELT, are designed to analyze the atmospheres of exoplanets, searching for these biosignatures. While the discovery of exoplanets has been revolutionary, identifying life beyond Earth remains an extraordinary challenge. The conditions necessary for life as we know it, liquid water, a stable climate, and the right chemical ingredients, are rare and difficult to confirm from vast distances. Moreover, life on other planets might be completely unlike life on Earth, potentially existing in forms or under conditions we cannot yet imagine. Another challenge is distinguishing between biological and non-biological sources of potential biosignatures. For example, methane can be produced by both living organisms and geological processes, requiring detailed analysis to determine its origin. The study of exoplanets goes beyond the search for life. It provides insights into how planets form and evolve, the diversity of planetary systems, and the conditions necessary for habitability. By studying exoplanets, scientists can better understand the processes that shaped our own solar system and the factors that allowed life to emerge on Earth. Exoplanet research also has profound philosophical implications, challenging us to reconsider our place in the cosmos. If life is discovered on another planet, it would fundamentally alter our understanding of the universe and our role within it. The discovery of exoplanets has opened an entirely new frontier in astronomy, bringing us closer to answering age-old questions about life beyond Earth. With advanced telescopes and innovative technologies, we are on the brink of unprecedented discoveries. Whether we find evidence of alien life or simply uncover more extraordinary worlds, the search for exoplanets reminds us of the vastness and diversity of the universe and the endless possibilities it holds. Space exploration is one of humanity's greatest endeavors, representing the drive to uncover the unknown and push the boundaries of what we can achieve. Over the past century, advancements in space technology have transformed our understanding of the universe, allowing us to explore planets, moons, asteroids, and beyond. From the first human-made object to leave Earth's atmosphere to the sophisticated rovers now roaming Mars, space exploration has not only expanded our knowledge, but also inspired generations to dream big. It is a story of innovation, perseverance, and the collective effort of humanity to reach for the stars. Space exploration began during the Cold War, fueled by the intense rivalry between the United States and the Soviet Union. The launch of Sputnik 1 by the Soviet Union on October 4, 1957, marked the beginning of the space age. This basketball-sized satellite was the first human-made object to orbit Earth, and its success sent shockwaves around the world. The United States quickly responded with its own space program, leading to a series of groundbreaking achievements. In 1961, the Soviet cosmonaut Yuri Gagarin became the first human to travel into space aboard Vostok 1. The United States followed with Alan Shepard, the first American in space, and later John Glenn, who became the first American to orbit Earth. The space race reached its pinnacle in 1969 when NASA's Apollo 11 mission landed humans on the Moon. Neil Armstrong and Buzz Aldrin became the first people to walk on the lunar surface, while Michael Collins piloted the command module in lunar orbit. These early milestones demonstrated humanity's ability to explore beyond our planet and laid the foundation for future missions. In recent decades, robotic missions have taken center stage in space exploration. These missions, which use probes, landers, and rovers, allow us to study distant worlds without the risks and costs of sending humans. Some of the most significant robotic missions include Voyager 1 and 2. Launched in 1977, the Voyager spacecraft explore the outer planets before continuing their journey into interstellar space. Voyager 1, now more than 14 billion miles from Earth, is the farthest human-made object from our planet. Mars rovers, NASA's Mars rover missions, including Spirit, Opportunity, Curiosity, and Perseverance, have provided invaluable insights into the geology and climate of the red planet. These rovers have discovered evidence of ancient rivers and lakes, suggesting that Mars may have once been habitable. Cassini-Huygens. This mission explored Saturn and its moons, including Titan, which has lakes of liquid methane, and Enceladus, which ejects water-rich plumes from its subsurface ocean. New Horizons. In 2015, New Horizons made history by flying past Pluto, revealing a surprisingly complex and active world. It later continued its journey into the Kuiper Belt, studying distant icy objects. James Webb Space Telescope, JWST, launched in 2021. JWST is the most advanced space observatory to date. It allows scientists to study the formation of galaxies, stars, and planets, as well as search for signs of life on distant exoplanets. The International Space Station, ISS, is one of humanity's greatest achievements in space exploration. Launched in 1998, the ISS is a collaborative effort involving NASA, Roscosmos, Russia, ESA, Europe, JAXA, Japan, and CSA, Canada. Orbiting Earth at an altitude of about 420 kilometers (260 miles), the ISS serves as a unique laboratory for scientific research and international cooperation. Astronauts aboard the ISS conduct experiments in microgravity, studying everything from human physiology to material science. The station has also served as a test bed for technologies that could be used in future missions to the Moon, Mars, and beyond. In recent years, private companies have revolutionized space exploration by reducing costs and increasing access to space. Companies like SpaceX, Blue Origin, and Rocket Lab are leading the way in commercial spaceflight. SpaceX, founded by Elon Musk, developed the Falcon 9, a reusable rocket that has significantly lowered the cost of launching satellites and supplies to space. SpaceX's Starship, currently in development, aims to enable human missions to Mars and beyond. Blue Origin, founded by Jeff Bezos, focuses on reusable rocket technology and plans to make space travel accessible to ordinary people. Virgin Galactic and Blue Origin are pioneering suborbital space tourism, offering civilians the opportunity to experience weightlessness and view Earth from space. Reusable rocket technology is a game changer, making space exploration more sustainable and affordable. Human exploration is entering a new era, with ambitious plans to return to the Moon and eventually send humans to Mars. Artemis Program. NASA's Artemis missions aim to return humans to the Moon by the mid-2020s, including the first woman and the first person of color. The program will establish a sustainable presence on the Moon, with plans to use it as a stepping stone for future missions to Mars. Mars exploration. NASA, SpaceX, and other organizations are working on technologies to enable human missions to Mars. Challenges include developing life support systems, radiation protection, and propulsion technologies for the long journey. Lunar and Martian bases. Establishing bases on the Moon and Mars could provide valuable insights into living and working on other planets. These bases may rely on resources like lunar water ice or Martian soil to produce fuel and building materials. The future of space exploration holds incredible promise. Advances in propulsion, such as nuclear thermal rockets and solar sails, could enable faster travel to distant worlds. Telescopes like the European Extremely Large Telescope, ELT, and missions like the Europa Clipper will delve deeper into the mysteries of the universe, from the search for extraterrestrial life to understanding the nature of dark matter and dark energy. The ultimate goal of space exploration is not just scientific discovery, but also ensuring the survival of humanity. Expanding into space could protect us from existential threats, such as asteroid impacts or environmental collapse, and unlock the vast resources of the cosmos. Space exploration is a testament to humanity's ingenuity, curiosity, and determination to overcome challenges. It connects us to the universe, reminding us of our small but significant place in the cosmos. As we venture farther into space, we continue to push the boundaries of what is possible, laying the groundwork for a future where humanity is a multi-planetary species. The journey to the stars has only just begun, and the possibilities are as limitless as the universe itself. The universe is filled with extraordinary and enigmatic phenomena that continue to captivate scientists and astronomers. From dazzling auroras on Earth to the mind-bending concepts of dark matter and parallel universes, the cosmos is a treasure trove of mysteries that challenge our understanding of physics and the nature of reality. These phenomena not only highlight the dynamic and unpredictable nature of the universe, but also serve as reminders of how much we still have to learn. One of the most beautiful and accessible cosmic phenomena is the aurora, often called the Northern Lights, Aurora Borealis, in the Northern Hemisphere, and the Southern Lights, Aurora Australis, in the Southern Hemisphere. These vibrant displays of light are caused by interactions between charged particles from the Sun and Earth's magnetic field. When solar wind, a stream of charged particles from the Sun, collides with Earth's magnetosphere, some of these particles are directed toward the polar regions. There, they interact with gases in the atmosphere, causing them to emit light. The specific colors of an aurora depend on the type of gas and altitude where the interaction occurs. Green auroras are caused by oxygen at lower altitudes, while red and blue auroras are caused by oxygen and nitrogen at higher altitudes. Auroras are not unique to Earth. They have also been observed on other planets with magnetic fields, such as Jupiter and Saturn. Studying these auroras provides insights into the magnetic environments and atmospheric compositions of these planets. Gamma-ray bursts, GRBs, are the most energetic explosions in the universe, releasing more energy in a few seconds than the Sun will emit in its entire lifetime. These bursts are thought to occur during two primary events. 1. The collapse of massive stars. When a massive star reaches the end of its life, it can explode as a supernova, forming a black hole or neutron star in the process. If the collapse generates powerful jets of energy directed toward Earth, we observe it as a gamma-ray burst. 2. Neutron star mergers. When two neutron stars collide, they release immense amounts of energy, including gamma rays. These mergers also produce gravitational waves, ripples in space-time that were first detected in 2015. Gamma-ray bursts are incredibly rare, but their detection provides valuable information about the formation of black holes, neutron stars, and the distribution of heavy elements like gold and platinum in the universe. Quasars are among the brightest objects in the universe, powered by supermassive black holes at the centers of distant galaxies. As gas and dust spiral into a black hole, they form an accretion disk, which heats up and emits intense radiation. Quasars can outshine the galaxies they reside in, making them visible from billions of light-years away. Quasars provide a window into the early universe, as many of them formed when galaxies were still young. By studying quasars, scientists can learn about the growth of supermassive black holes and the evolution of galaxies over cosmic time. One of the newest cosmic mysteries is fast radio bursts, FRBs, intense, millisecond-long bursts of radio waves that originate from distant galaxies. The exact cause of FRBs remains unknown, though some theories suggest they may be related to magnetars, highly magnetized neutron stars, merging black holes, or even advanced alien civilizations. FRBs are challenging to study because they occur randomly and fade quickly, but advances in radio telescopes have allowed astronomers to detect more of these elusive signals. Understanding FRBs could reveal new physics and shed light on the most extreme environments in the universe. While visible matter, like stars and galaxies, forms the familiar structures of the cosmos, it makes up only about 5% of the universe's total mass energy content. The rest is composed of dark matter, 27%, and dark energy, 68%, two mysterious components that remain poorly understood. Dark matter. This invisible substance does not emit, absorb, or reflect light, making it detectable only through its gravitational effects. Dark matter is essential for explaining the rotation of galaxies and the large-scale structure of the universe, but its true nature remains one of the greatest unsolved mysteries in science. Dark energy. Discovered in the late 1990s, dark energy is the force driving the accelerating expansion of the universe. Its nature is even more mysterious than dark matter, but it plays a crucial role in shaping the ultimate fate of the cosmos. The concept of the multiverse suggests that our universe is just one of countless others, each with its own physical laws and properties. While the idea is speculative, it arises from theories in quantum mechanics, string theory, and cosmology. If true, the multiverse would fundamentally alter our understanding of reality and provide new explanations for why our universe appears fine-tuned for life. Evidence for the multiverse remains elusive, but it continues to capture the imagination of scientists and the public alike. The cosmic microwave background, CMB, is the faint glow of radiation left over from the Big Bang, providing a snapshot of the universe as it was about 380,000 years after its formation. This relic radiation is one of the most important tools for studying the early universe, offering insights into its composition, structure, and age. Detailed measurements of the CMB, such as those made by the Planck satellite, have confirmed key aspects of the Big Bang theory and revealed the subtle fluctuations that led to the formation of galaxies. First predicted by Einstein's general theory of relativity, gravitational waves are ripples in the fabric of space-time caused by massive cosmic events like black hole mergers or neutron star collisions. The first direct detection of gravitational waves in 2015 by LIGO marked a new era in astronomy, allowing scientists to study the universe in a completely new way. Gravitational wave observatories are now detecting these events regularly, providing insights into the most extreme objects in the cosmos and confirming predictions of relativity. The universe is full of phenomena that stretch the boundaries of our knowledge and imagination. From the violent explosions of gamma-ray bursts to the invisible forces of dark matter and dark energy, these cosmic mysteries remind us of how much there is still to explore. As technology advances and our understanding deepens, we move closer to unraveling these enigmas, shedding light on the vast and wondrous universe we call home. The future of space exploration is a bold and ambitious endeavor, pushing humanity to expand its presence beyond Earth and explore the farthest reaches of the cosmos. With advancing technologies and international collaborations, the possibilities for discovery and colonization have never been greater. From returning to the Moon to establishing human settlements on Mars, space exploration is entering a new era, driven by both government agencies and private enterprises. This quest to reach the stars not only seeks to answer fundamental questions about the universe, but also aims to ensure the long-term survival of humanity. One of the most immediate goals in space exploration is a return to the Moon through NASA's Artemis program. Unlike the Apollo missions of the 1960s and 70s, which were short-term visits, Artemis aims to establish a sustainable human presence on the Moon by the end of the decade. The key objectives include landing the first woman and the first person of color on the lunar surface, building the Lunar Gateway, a space station orbiting the Moon to serve as a staging point for lunar missions, conducting research to understand the Moon's resources, such as water ice and permanently shadowed craters, which can be used for drinking water, oxygen production, and rocket fuel. The Moon is seen as a stepping stone for deeper space exploration, including eventual missions to Mars. Mars has become the focal point of human exploration beyond the moon. With its potential for habitability and resources, the red planet represents humanity's best chance for establishing a self-sustaining colony. Key plans include NASA's goal of sending humans to Mars in the 2030s, using technologies developed through Artemis and robotic missions like Perseverance and Curiosity. SpaceX's Starship program, spearheaded by Elon Musk, aims to create a fleet of reusable rockets capable of transporting humans and cargo to Mars, with the ultimate goal of making humanity a multiplanetary species. Addressing challenges such as radiation exposure, the need for life support systems, and the psychological effects of long-duration space travel. Mars colonization is seen as a critical step for ensuring humanity's survival in the event of a global catastrophe on Earth. The search for extraterrestrial life remains one of the most compelling motivations for space exploration. Upcoming missions and technologies aim to explore key targets in our solar system and beyond. Europa Clipper and JUICE missions. These missions will study Europa and Ganymede, icy moons of Jupiter with subsurface oceans, thought to have the potential to harbor life. Enceladus, a moon of Saturn, known for its water-rich plumes. Enceladus is another prime candidate for astrobiological research. Interstellar exploration. Concepts such as Breakthrough Starshot, which aims to send tiny, light-powered probes to Alpha Centauri, our nearest star system, represent humanity's first steps toward exploring beyond the solar system. The rise of private companies has transformed the landscape of space exploration, making it more accessible and cost-effective. Companies like SpaceX, Blue Origin, and Virgin Galactic are not only advancing technology, but also creating new opportunities for space tourism, asteroid mining, and orbital manufacturing. Space tourism. Suborbital flights by Virgin Galactic and orbital trips by SpaceX are opening space to private citizens. Asteroid mining. The extraction of valuable resources like water, metals, and rare minerals from asteroids could support both space colonization and Earth's economy. Commercial space stations. As the International Space Station nears the end of its operational life, private companies are developing replacement stations to support scientific research and industrial activity in low Earth orbit. While interstellar travel remains a distant dream, scientists are exploring theoretical propulsion systems like nuclear fusion rockets, antimatter drives, and warp technology that could one day allow humanity to reach other star systems. Projects like Breakthrough Starshot and advancements in exoplanet detection are laying the groundwork for exploring habitable worlds beyond our solar system. The future of space exploration is filled with limitless potential, driven by humanity's innate curiosity and desire to explore. From returning to the moon to colonizing Mars and venturing into interstellar space, these efforts will redefine our understanding of the universe and our place within it. As technology advances and international collaboration grows, space exploration is poised to become a defining chapter in the story of humanity, a chapter that will inspire generations to come.